Hello, everyone. Thanks for joining the session. We are very excited to share some of the observations and the learnings we had building multimodal agentic RAG using OpenSearch and a few other AWS services. Before we get started, quick intro. My name is Mohammed. I'm one of the product managers on the OpenSearch service team. I particularly work on the GenAI and some of the agentic initiatives. Surya, you want to do a quick intro?
Yeah, so my name is Surya Kari. I am a senior generative AI data scientist on the SageMaker team within AWS, and I'm excited to be here. I hope you guys enjoy the talk.
All right, cool. So I think we got about 40 minutes for this session. So first 25, 30 minutes, we're going to spend on some basics of RAG and how it is evolving. And we're going to share what we built as a multimodal agentic RAG solution. And quickly we'll follow with a demo, and we'll take some Q&A at the end. Please hold your questions until the end. Love to have the discussion and address any questions you have. We plan to stay hangover after the session. If you have any questions, happy to have one-on-one discussions as well. Okay. With that, let's get started. So it is a snapshot of what we built. Basically, it's a multimodal agentic RAG. There are the focus areas are on two areas. One is the multimodal and the agentic. To be simple, in simple terms, basically, we are trying to do a RAG which is beyond text only. We are taking basically input as text in image, audio, and video. In our use case, we focused on text and image, and we are using agentic orchestration layer to manage the tools that really deploys the RAG implementation. So before we get started, we show that in action. Let's go through some of the basics we want to cover and level set the concepts and the architecture that we built for this solution. One of the good things that comes with the job we have is we get to talk to hundreds of enterprise customers who are building very advanced GenAI use cases. And when we talk to these customers, most often we hear that they're having challenges bringing RAG use cases to production. And more we dig on that, we find that primary challenge we find that is they focus quite a bit on picking the latest and greatest language models and less so on the system approach. How do we focus a lot on retrieval and what kind of data prep we do? How do we optimize all these things in a systematic approach so that you get best out of the models and the retrieval and other components within the RAG system? And if you really look at LLMs, they are very smart. They're getting smarter day by day, but they are meant for very generic search, right? So they cannot address very specific problems, and they don't have the context that you're looking for a particular use case. So that's where there are some limitations that we see with the LLMs, and these are some of the most popular limitations called out. If you look at it, basically, most of these models are trained in a particular period of time, so they're stuck in time, and they hallucinate. Basically, they pretend they're giving the right answer, and also they are kind of trained on a particular data set, and you got to fine-tune to make it applicable to your own domain-specific tasks. And also, they are very limited in context, right? So first thing, they don't have the enterprise context. And the second problem is the context window of these LLMs is very limited. And the answer to that is RAG, right? So RAG is, in my view, it's basically a framework that can solve any problem with infinite context for that specific use case. So there are basically, if you look at RAG at a highest level, you have 3 to 4 key components, as you can see. It looks very simple, but as you double click on this RAG solution, the complexity involved is a lot. So in each basically key component, there are multiple steps and the knobs that you need to look at. and understand them and tune them to get the best out of these RAG system. And that means the people who are working on it, they need to have the deep expertise to understand the retrieval concepts. They need to understand how the large language models work. And also they need to understand how they do the data processing and also the indexing. There are many concepts that cut across different expertise areas, and very few people can cover that kind of a breadth. So usually it's an expertise gap, and in the process of fixing this, it becomes very iterative and it gets very costly. So if you really look at RAG, right? So a traditional RAG, basically you have to deal with volumes of unstructured data, and when we talk to our customers, we see petabytes, if not terabytes of data very often. How do you deal with this messy unstructured data, and do you do the document parsing and get the right data? And on top of it, how can you do the system optimizations to get the best settings and the configurations to get the right accuracy for you? And in the process of that iterations, people end up spending a lot more development cycles, and the cost of ownership goes up quite a bit. And if you layer this on top of the whole stack that goes into deploying a RAG solution, traditional one, you see primarily I see 3 layers. The bottom one is the compute infrastructure, where if you take OpenSearch kind of a platform, you need to know how do you optimize your clusters, what kind of instances you pick, or do you want to do GPU acceleration or CPU acceleration is enough. So there are a lot of trade-offs you need to make. On top of that, you need to think about your modeling layer, what kind of embedding models you pick, and how do you think about re-rankers, all that stuff. And you have the usual complexity and the tricks that you need to apply to bring these all things together. So that's where the agents come into play. You can pretty much take care of the top layer using the smartest LLMs out there. They're getting better and better every day. So the key point here is, I think the future of future of RAG is going to be very much driven by the models, which are very powerful, very smart, and they can do dynamic optimizations, make a bunch of decisions on your behalf, and that's where the agentic frameworks play a big role. So if you look at why agents for RAG, right? So see, traditional RAG is very powerful. You can ask any query, pretty much they can answer, but the accuracy may not be where you want to be. But if you apply agentic orchestration layer on top of it, and you can build multiple tools for a specific task. For example, in a real world, the queries that you get are very messy, and sometimes you need to rewrite those queries and clean up so that the LLMs can understand and process them better. And also the context awareness is very important. History of the conversations or the history of that particular use case, knowing how do you deal with the memory and having some kind of tools that can deal with the agents is very helpful. And also there are a bunch of retrieval types that you can think about to solve these problems and get this similar accuracy. And on the outcome of this is using agents on top of RAG framework would be like you have very efficient decision making that's very iterative and self-correcting. And instead of having a static pipeline, you will have a very dynamic pipeline where you have multi-hop reasoning, all that stuff, because you are using agents on top of RAG framework. So there are a bunch of benefits. It will be like you can handle the context much better. That means you're having very high accuracy in your answers. So if you put together all the solution that we built, this is how it looks. Essentially, we built a bunch of tools that agent can access. We built an embedding tool where it can process multimodal embedding data, and then we built a query tool on top of it. We also built a retrieval tool that can decide between different search types, between lexical, semantic, or hybrid search. And on top of it, how do you deal with multimodal input that comes to the system? So we have built evaluation tool. How do you make sure the quality of the RAG outputs are looking nice? So we kind of invested there. So overall, once the query comes, we kind of have a multi-agent orchestrator that dynamically picks what is the right tool to use and based on the outputs it's getting, it kind of iterates and processes the data and then works with the vector database to store those embeddings and then retrieve the right information. So to kind of solve this problem, we kind of use primarily three services for vector database, OpenSearch. And then for multi-agent orchestrator, we used AWS Strands, which is an open source framework that recently hit like 1 million downloads, being adopted widely by number of developers. And then for the endpoint and to deal with generative models that are open source, we used Amazon SageMaker AI. So using this collection of services, we were able to put together a solution that gives you a highly accurate answers for your questions and answers. So if you further double click on the ingestion pipeline, this is how it looks. Essentially, we built a tool called embedding tool that an agent can access, which will do the metadata extraction so that you can apply some kind of filtering, and that will help you to do efficient search. And also, it can extract the text and image that you are inputting as a multimodal input. And before that, we have a document parser we use to kind of convert the unstructured data into structured data. And we used a very fixed chunking and a HNSW indexing algorithm to kind of take care of this ingestion. So the retrieval is as good as your ingestion data. So if you can manage your inputting and a clean data ingested at scale, then the quality and the reliability of the retrieval will be in parallel with that. Okay. So multimodal embedding, right? So when we do the ingestion, we kind of decided to use work with the image and text multimodal data. Historically, before the multimodal embedding models were there, people used to use multiple vector stores to store the text embeddings and then the image embeddings, and then they do the post-processing to combine the embedding space. But with the latest advancements in the modern foundation models, we have the multimodal embedding models, which will have a single vector space where you can have the combined vector space where you see the semantic relationship between all these modalities. So we use the multimodal embedding model in our use case and try to see, we kind of see better results with that. Of course, there is a trade-off with cost. Usually multimodal embedding models are a little bit pricier, but the performance and the accuracy that you get out of it kind of outweighs the cost that comes with it, okay? And then this is how the retrieval pipeline looks like. We basically used built a retrieval tool where the Strands orchestrator will talk to that and make a decision based on the query, and it runs a different kind of search technique, lexical, semantic, or hybrid search that comes with the OpenSearch vector database. And based on the accuracy and the query type, it will pick the right one for the particular query. And basically, it goes through a re-ranker to determine, reorder the results. And basically, you have a summarized answer from that, okay? So we built a MCP server to solve this problem of OpenSearch MCP server. So I'll let Surya to take it from here. Okay.
Yeah. Thank you. Thank you, everybody. Right, so we were talking about tools specifically designed to do one very specific task. Bobby was mentioning that. So the way we've designed the OpenSearch MCP server was the MCP OpenSearch server would be responsible for ingestion of the data. It would also be responsible for retrievals. And an agent would intelligently call upon the MCP server to either ingest data or retrieve data based on the query that is posted to the orchestrator. For the multimodal embedding model, we actually used Qwen 2.5 VL that we hosted on SageMaker AI. It's a really good model for visual and textual information. It essentially, you're able to use that as a great generation model. You can give it a text input, you can give it a visual input, and I'll actually do a demo, and you'll see what I'm talking about. It is a unified vision language architecture, so it does have a lot of that advantages. It can be used in visual question answering, chart diagram analysis, document understanding. Just a little bit about before I go. Before I go further, I'll talk about the data set we've used as well. So we used Visual QA, VQA, which is the data set that is open source, and it has a very permissive license. The VQA data set is essentially a bunch of documents that have, not very dissimilar to what enterprises have, right? Enterprises have documents that have text in them, they have charts in them, they have images in them. And if you convert all of them into a single modality, like say text, there's a lot of information loss. So we took that as a challenge and we said, hey, what about taking these documents and being able to do multimodal embeddings from them and then converting that into a multimodal RAG pipeline. So I just want to give you an understanding of the data set. So it's VQA. The embedding model that we used is the Titan image embed V1. So what this does is it converts images and text into the same embedding space, and it is essentially, if you want a really nimble, really lightweight model that is openly available, that is readily available on, it's a frontier model that you can access immediately. This is a great model to start with for your multimodal journey. It enables real-time embedding generation. It enables highly accurate semantic understanding. And there's very little information loss when you're trying to combine modalities into one embedding space. Right, so before I go into the demo, these are some of the evaluation results we've seen. So we've evaluated it across multiple retrieval metrics and relevance and completeness metrics. These are not very dissimilar to what RAGas would put out, but we actually created our own base class. We actually created our own RAGas class for multimodal evaluations using the RAGas base class that it provides. So we actually retrofitted RAGas to do multimodal retrieval analysis because RAGas by default only does text evaluations. So what we've seen is the top relevance score, the precision at 1 has always been 100% with the VQA data with multimodal embeddings. The sub 3-second response time has been almost 70% of all of our queries have a sub 3-second response time. And our response latency is generally around 3.7 seconds for pretty much every query that we had. And you could see that the retrieval metrics in terms of precision is actually quite high. And if you compare this to, say, a text-based retrieval, a lot of the text-based queries in VQA just won't even work with this because VQA is a data set that is specifically built for multimodal queries anyways. And I'll show you the database, the data set as well. But without multimodal queries, the entire data set would actually not even work. I'll do a quick demo here. And then if you guys have any questions, I'm happy to take that on. There's actually two different things that I want to show you here. So let's just look at this picture, right? So this picture has somebody skateboarding, people watching, and we can say, hey, where is this person looking, right? And it goes, analyzes the picture, it creates the embeddings, it then queries the MCP server, and then says, find me relevant information based on this image. And then it retrieves all of these information from the from the OpenSearch database that we've created, right? So all of this is retrieved from the OpenSearch vector database, and then based on that, this is so you could see that it's formed a query. It's essentially taken the embeddings, formed a query. It has retrieved all of this from the database, and you could see that the vector similarity searches are around 97%. And you could see what it says, right? It says the answer is down. He's looking down. Actually, there's another more compelling example that we can give. So this is a much more, so you could see this soup here, and we can say, describe the soup. Right, again, it converts it into embeddings. It queries, so we have an orchestrator that takes the query. It then hands it off to another agent. The agent then queries the OpenSearch database using the OpenSearch MCP server. It then retrieves all of these knowledge from the knowledge base, and then it tells you the soup is a creamy noodle soup. So because the questions are, is this a rice noodle soup? It appears to be Japanese, so it does take what's from the database, but it also then takes that to the generation model. The generation model then adds its own flavor to it. This is another demo that we've created. We couldn't actually host two different demos on the same port, so we had to do this. But you could see here that with text-based VQA chat, so we're going to do, let me actually do a quick playback speed. So you could see that with no image, like no multimodal context, if we just say, where is he looking? It'll give you a wrong answer because the query from the database has failed. It just gives you wrong answers. But with the image being given, the multimodal context being given, it retrieves the right information, and then it gives you the right answer. So the question itself needs to be multimodal, and it is in these kind of situations that you need a multimodal approach to your data, and that's what we're trying to show here. We are actually going to write a blog on this in the next couple of weeks. We're going to be including a lot more information about the architecture. We're also going to be including a lot more information about our own approach, the code. Everything will be public for all of you to use. In the meantime, that should be I think we have one more slide here. So again, so the key takeaway is traditional RAG is complex, it is not extensible, and it is not enough. Agentic RAG, essentially, it unlocks more use cases. It also improves accuracy. Agentic RAG coupled with multimodal capabilities delivers higher accuracy. It also helps enterprises look at their own data in a different lens. And agentic workflows with RAG essentially lower the amount of hallucinations that a generation model might introduce into your own data. So having that answers grounded in your own data is actually very helpful, and it lowers hallucinations. That is the end of the demo, and that is the end of my talk. I'm happy to take any questions if you have any. Yes, sir.
I didn't get what the agent is doing.
Right. So there are two agents here. So there's an orchestrator agent that takes the query, and then the orchestrator agent then hands it over to an agent that is dealing with the OpenSearch MCP server, right? The OpenSearch agent essentially understands what the query is doing.
It's a query understanding agent.
Correct, and it does multiple things. So there's an LLM that is powering it, which is the Claude 4 there's a Claude 4 model that is hosted on Bedrock. We use that. So what it does is it does a couple of things. Number one is it understands if the query is, hey, I want you to take this either take this query and then retrieve something from the OpenSearch MCP server, or we also have the ability to give data and then it'll ingest it into the OpenSearch vector database. So it understands what it needs to do based on the query itself. Essentially, in our case, what it essentially does is it takes the query, converts it into the same embedding space as the other data that we've ingested into the OpenSearch vector database, and then it queries that database using those embeddings. Again, remember that text and images have the same embedding space. So you can query your database based on the embeddings that have been created. Each embedding has some amount of metadata connected to it, and that metadata is then surfaced back to a Qwen2 VL model. That is, again, something the orchestrator does. So the orchestrator essentially has two different tasks here. Number one is giving whatever it gets to the agent that is dealing with the OpenSearch MCP server, and also taking what's coming back from the OpenSearch MCP server-based agent, and then giving that to the Qwen2 VL, which is the generation model, and then surfacing whatever is the response from the Qwen2 VL. So there's two different agents here. It's not a very complex system, but we have two different agents in this entire workspace. So sorry, yep.
Yeah, so there's a class, and you talk about the vector case. Let's think about the simple case, the lexical case. So in the lexical case, you have a query with, say, like red pumps.
Mm-hmm.
And that's ambiguous. It can mean water moving equipment that's colored red, or it can mean women's high-heel shoes that are red.
That makes sense, yeah.
Does your system now say, I want to look for either women's shoes or pumps? What sort of transformations is it doing on the query?
Right, so if your query is, tell me about red pumps, right? Now imagine if your data is more about, there's a lot of data in your vector database about red pumps that pump water, right? But you really want to understand, hey, what about women's shoes which are red pumps? With just textual understanding, it would retrieve, possibly, and I'm not saying that this is what it's going to do, but it would possibly retrieve the first hit it would get in terms of like red pumps that would pump water, because that would be the first, because it's a greedy search. If a lot of your data is essentially just about red pumps that are water pumping, it would just retrieve all of that and then give it to you, because it doesn't have the contextual understanding that it would just be. So if you give it, hey, give me red pumps that look like what's in this picture, then it would be, then that makes sense. So it wouldn't fail, because again, remember that all of these are in the same embedding space, so it wouldn't fail because the embeddings would be the same. The data retrieved would probably not be as good in quality, because it just would retrieve the wrong data, because it's not. Yes, please. Yeah. Anybody else? Going once? And twice?
Okay.
All right.
I'll give you another one.
Oh, sorry. Yeah. Okay.
So you were saying precision at 1 was 100%.
Yes.
But without knowing how many correct answers there are in the corpus, that's hard to interpret.
I mean, there's only one. It's a VQA comes with its own ground truth.
So, but the man could have been looking down, or he could have been looking at the table, or he could have been looking at the floor. And I can see the picture very clearly. All three of those seem like correct answers.
I mean, the question was, where is the man looking? It's not what is the man looking at. So we could try it really quickly. Like we could say, is it even working? You see, the man is looking at the escape.
Okay.
Whoops.
He is the skateboarder.
He is a skateboarder. Yeah, so, I mean, at the end of the day, these are two different questions, is what I was trying to say.
Okay.
I mean, it would, and the ground truth for VQA is very clear. The question, where is the man looking, has a single answer in VQA. And that's the great thing about VQA is the ground truth is, it's very clear, which is why we could calculate things like precision at K in the first place, because we could compare it to the ground truth. So these are actually what's in the ground truth. So these come straight from VQA. So, and we use the same questions to calculate our own precision metrics. So we don't really go outside of the questions that are provided in VQA anyways. Any other questions? Awesome. Thank you, everybody. I think we're at time. Thank you.